Oh yeah, we're ready, yeah.
All right, we're going to get started. Thank you all for coming. My name is Noam Zilberstein. I'm one of the organizers of the workshop. So before we get into the keynote, I just want to say a few words about what this workshop is about. It's about incorrectness. Obviously, incorrectness has existed for a long time. Since programs existed, there have been incorrect ones. But it wasn't until about 4 or 5 years ago that people started to really seriously think about formal methods for proving that programs are incorrect. And of course, all of that started with Peter O'Hearn and a few others. So in order to set the stage, we're going to have Peter talk about his journey, his realization that incorrectness is an interesting and important thing to study. And then throughout the day, we'll see more applications, more ways that people start thinking about formally reasoning about incorrectness in new areas that aren't just about, not just program logics, but also things like types, hyperproperties, and all kinds of other great stuff. So with that, I will hand it over to Peter for the keynote.
Thank you. Okay, so what I wanted to do today is to emphasize a couple of things. So first, when I moved from academia to industry, I bumped into a whole host of new problems. And when I was stepping back and thinking about it, when I grew up as an academic, there was a certain set of assumptions. And the kinds of assumptions you would have coming from some of the greats of program logic. Well, you should write your specification first, and then you should write your program. You should write your loop invariant, and then derive all these kinds of things. And then when I moved to industry, this was violently at odds with the way things were working. And they had some reasons that made some sense for why it was violent. And I thought, maybe our assumptions, we should revisit those. Maybe our assumptions are more like religious beliefs than scientific things. So I was thinking about that. And then eventually I got onto this paper I wrote in 2020, Incorrectness logic. Now, when I wrote that paper, I was really influenced by Hoare. So Hoare created lots of simple things. The one thing he always did in his papers is he tried to write it as simply as possible, so as many people as possible could read it and understand it. And what I didn't want to do is I wanted to remove as much theory as possible from the paper that I wrote on incorrectness logic. And I think I succeeded in that. I don't know that I made any technical contribution in that paper, right? It was sort of a survey piece or a synthesis piece based on a whole bunch of stuff that was sort of known. It's like, well, maybe we could put things together in this somewhat nice way and explain the motivations for why you would want to do so. But as I was writing it, I didn't really think there was hardly any technical contribution. But there's real value, I'm not saying for one paper, real value in explaining things simply and putting things together in a way that people understand. And I thought this is one of Hoare's, the great things that Hoare did. What I thought I would do here now, because I've got an audience of people who are more into the formal side, I want to tell you some of the thought process behind the incorrectness logic that I didn't want to write in that paper. So we'll see if that's useful to people. So in the beginning, when I was still proving programs correct only, I still love proving programs correct, by the way, and I'm working on that now, but in the beginning, for us, there was some people in London, that's Dino and Cristiano, myself and Hong Suk, working on crazy program analysis. And this is one of our early papers. And this was proving memory safety of device drivers. And so here I was really influenced by the SLAM project. So the SLAM project proved properties of real device drivers. But we worked with Byron Cook, who told us all of the weak points of SLAM. And the major weak points is that SLAM assumed memory safety. So it only proved it, assuming that there were no bugs of the memory safety variety, but there were, right? And so we thought, we've got some memory analysis techniques, let's have a go at those. And so then we found some bugs in the drivers, we proved them correct, or free of memory safety errors with respect to certain assumptions. And so this was pretty good. So this exceeded what I ever thought I would do in the practical realm as an academic, because, I mean, there's 10,000 lines of code. Bugs were fixed inside Microsoft as a result of what we found. So I was very happy. I thought this is really good. But then there was this other person we were working with, Cristiano. And Cristiano was very unhappy with these results, right? Cristiano said, well, how many companies have little discrete 10,000 line programs that are that important? Not that many, maybe Microsoft, but not that many companies. He says, what if we want our program analysis techniques to influence like lots of companies, lots of code around the world? He said, he put it more strongly, this is completely useless. The way Cristiano put it. This was the best possible results that I thought I could aim for, and he's saying this is completely useless. And so then he had written on his blackboard at Imperial College, go huge or go home. If you don't have a million lines of code that you're covering, then he didn't want to hear about it. Right? So he wanted to get to a million lines of code. And he asked me, well, how can we get to a million lines of code? And I realized that the big problem in applying these techniques was that we need to discover a precondition when we're analyzing a procedure in order to get to the post. And usually the human discovers it, or we do it in some top-down way. And then I said, well, what we need to do is we need the analysis to discover the precondition, then we can find a post. Then we'll be able to make a compositional program analysis. And so I hypothesized that we'll get something running on big code. And we did, and okay. So by abduction is one way to forwardly analyze the program and throw some information back to the pre. You get a pre, which is going to guarantee memory safety under certain assumptions. Then you get a post. And this ended up giving you a way to have a very scalable program analysis. And so then we published it in POPL. And the POPL referees loved it. And we emphasized the scalability, which was there. And we emphasized that we had proven memory safety with respect to assumptions of a certain number of the procedures. We also found some bugs, but we didn't emphasize that. So this was all good. So writing the paper for the POPL audience. So this even won the 10-year retrospective award from POPL. I don't know if it was for trying to prove things, but we thought that the POPL audience liked this aspect. But then when we went out and we started talking to other groups of people, we were forming a company based on this because finally it could scale. What people got excited about wasn't proofs of memory safety. Like Dino used to give a demo. Dino would, at the start of the talk, run an OpenSSL. Because it was a scalable program analysis, by the end of the talk, he would run it on OpenSSL. By the end of the talk, we had analyzed the entirety of the OpenSSL and found 72 memory leaks, potential memory leaks. Then, on the spot, he would fix a memory leak and rerun the analysis, and within like seconds, it would confirm that this fix was okay. So it was incremental. And so then you could see that it was, maybe we could put this into the software development process. So people loved the scalability and the incrementality of it. So much so that the reaction in other audiences was quite different. We gave talk at Industrial Security Conference. And when he did this, somebody in the front of the audience jumped up and cheered. Right? They said, yay! Because they couldn't believe that with all these formal methods, people are all of a sudden doing things incrementally. So that the fastness was very important. The incrementality was very important. So we made a company. Eventually, the company was acquired by Facebook. And we went to work at this company, Facebook, and there's this hack logo on the floor or at Facebook outdoors. But why did Facebook decide to buy it? No, it didn't. We had program verification people going into the company with this emphasizing hack, right? They loved the scale of Infer, the fact that they made us, when they interviewed us, they made us run it on the Android OS, and it completed. Just that it completed, they were amazed because many tools don't complete. It was incremental. They could see, this is going to work for pull request-based commenting. They could see better than us. They hated giving bug lists. They had tried many static analysis tools that gave bug lists. This was always a failure mode. The developers hated it. It did find real bugs. So we ran it on some internal Facebook code bases, smaller than the millions. And one of the Facebook code bases, it found some bugs. And these bugs were in a code base that happened to have been written by hero programmers inside the company. So the people interviewing us thought, this is hilarious, right? Like, this tool has found bugs in the code written by the hero programmers. So then they're very excited by that. Apparently they liked me, Cristiano and the team. What they didn't comment on was proofs of absence of bugs. They absolutely didn't comment on it, right? We emphasized it over and over again. And they said, okay. But when we showed them bugs of the hero programmers, then they were extremely excited. So I worked for a while, right? We worked for a while deploying Infer. So I hadn't decided I wanted to work on Under-Approximation or anything at this point. So then I worked for a while. I was the manager of the Infer team. Somebody had to manage the team. That fell to me. Then after about 3 years, I was getting extremely bored, and I wanted to work on technical problems. So we arranged for me to move to the to the engineer track, and somebody else to manage the team. And I said to my manager, who's a VP, Brian Sullivan, okay, I'm giving it up. And so for my first task, I'd like to try making a concurrency analysis that can scale to people in the company, work for the people in the company. And I wanted to prove some code. He said, that's so good. This was really great. He wasn't saying, what was really great is he wasn't saying, what's the return on investment? He said, well, that's a hard problem, but the worst would probably be useful. Go for it. So I had my goal. I wanted to prove hundreds of thousands of lines of code race-free in the Android app at Facebook. So that's what I took as my goal. So I didn't want to do a 10,000 line device driver. Now I wanted to use concurrency proofs of hundreds of thousands of lines of code, hopefully millions of lines of code. So I thought this was a good goal. And I was very charged up about it. And the context at the time was this. So one of the important papers on race detection was by Engler and Ashcroft. And we all know that Engler is very good at, Engler's one of the people behind Coverity. He's very good at analyzing systems programs and finding problems. Now, they found 3 race bugs in Linux, right? This was a good paper, but there's many more than 3 race bugs in Linux, right? They're missing lots. If I worked on this problem at Facebook for a year and found 3 race bugs, I might have been giving my marching orders, right? This wouldn't be good enough. They're great people, but the reaction of this by people in industry, other great people are Sarah Branyan colleagues who made this dynamic race detector. The reaction in the community was that static race detection is too difficult. We need to go dynamic as a consequence. So they made this dynamic race detection, which is very useful and is deployed in production in a number of companies. And it's called Thread Sanitizer. And so that was the idea. And so of course, so for me, this is no problem, right? It's like, okay, so everybody thought it's too difficult, so why not have it go, right? After all, we had concurrent separation logic in our back pocket, and I was very cocky. I thought, I've got to go for this problem. I don't care that people thought it was too difficult, right? Concurrent separation logic, I think I can scalably reason about code, so concurrent code. So I spent some time, right? What I did is in industry, when you attack a problem, you don't just build the analyzer, you need to understand the context. So I stared at thousands and thousands of lines of the Java code, the Android code of Facebook, to try to understand its character, and then try to figure out what would a really good prover/analyzer look like for this style of code. I did mental proofs about the code. And these mental proofs means I sketched out the program logic proof. I decided that 95% of the code I could knock it over with something called fractional permissions with concurrent separation logic. I designed an algorithm, a pen and paper algorithm for discovering all of the invariants. The other 5% was very fine range concurrency. And I thought, I'll get to that later, right? I want to get that 95%. That'll get me to my hundreds and hundreds of thousands of lines of code. And I started writing a prototype. And this was very, very, very fun. So the kind of thing I did in my prototype, although I had an algorithm to infer what's called resource invariance, I didn't implement the algorithm first. The first thing I implemented was how to find some dead obvious races and report them so the programmers understand, because I realized that, well, if I'm ever to succeed deploying this, I've got to have good error messages, number one. And number two, I as a theorist, I'm a lot better at figuring out how to do an algorithm for proof then I'm figuring out how to give good error messages. So I thought, well, let's concentrate on the thing that I'm not that good at, giving error messages, before the thing that I'm better at, is algorithms for doing proofs. So I decided to find some obvious races where you've got to write outside of any sync. Forget about logic+, just any sync. And so in the first case, I've got the true positive self race. If I run that in parallel with itself, right, it's going to be a race. The second one, if I run this in parallel with itself, it's not going to be a race. So I would want to figure out things like that. The third one, it wasn't that trivial. So I looked for, I wanted accesses that are syntactically identical in two threads. So I didn't want to do lots of alias analysis and things like this. Syntactically identical accesses in two threads, which would tell me obviously there's a race. The third case, we would have syntactically identical accesses, but it happens to be freshly allocated. So in the third case, if I run that with itself, you're not going to get a race, right? Because you're going to get new. And so you had to take care of some extra things. So it's not quite as easy as I was saying, but fairly easy cases I try to get. And so I was finding things in the Android code base based on this. Then, and I was having the time of my life, right? So because I was a professor before going to Facebook, I never wrote any real code, right? So the only code I wrote was for the programming language classes. Like I would write an interpreter, give it to the students, ask them to change it. But I never wrote any code that somebody else used, right? And I didn't know really. I'd never done any software engineering. So this was really fun because this was my first software engineering. And I got to only 1,000 lines of code, not very much. So I was sort of celebrating, oh my God, I'm getting to 1,000 lines of code. And this was really fun. I was writing in OCaml, which is an absolute pleasure of a programming language, right? Functional programming, the most beautiful type system. Now all of industry is finally catching up with OCaml, with all these programming languages that are very much like OCaml with different syntax. But then this fellow Sam Blackshear, who was mentoring me, I was his mentor when I was a manager, that when I switched to be a programmer, he was my mentor because he knew how to program, right? So he was my mentor. But then we used to write updates to the Android community at Facebook, which is a couple of hundred programmers. And in his update, he said, there's this fancier concurrency analysis checking that the classes marked thread safe are actually thread safe. And I took this to mean if they say they want this class to be thread safe, it means all of the public methods don't race with one another. That's what I took that to. That was the theoretical approximation of that concept of thread safe that I was taking. And people started asking questions, right? Like, will it be recursive? They were asking, is it going to be an interprocedural program analysis in our terms? And this is, well, there's some reasons, but they needed it to be interprocedural or it was a non-starter. So when Sam asked that question, I said, oh shit, right? Because when you're trying to do something, like I wanted to make a proof for hundreds of thousands of lines of code, and I thought, this is very hard, but I thought I could get there in about a year, right? I thought I could get this really good thing. My plan was to get there in a year, and then they're saying, we need this now. And I said, oh my God. And so then I didn't respond to any of the first things people said, and I was hoping that they weren't going to say anything else, so I could get back to my nice plan of making my concurrent separation logic proof, right? Then I started getting other messages, like this was from a fellow in New York, and he says how he heard we're working on this, it could dramatically help us in our plans. And so then what am I going to do? Am I going to tell them no? But on the other hand, you've got a team, they were working on something that's important. They needed to take the Android app and convert it so that it was multi-threaded in order to speed it up. Now they're taking a huge sequential code base and converting it to be multi-threaded. Now guess what? There's going to be tons of data races if you try to do that. And their only way of dealing with this was to mentally walk through the code and try to figure out the so it was problem. So they needed this. So then I can tell them, no, I'm not going to help you out because I've got to make my beautiful prover. Or I can say, well, for business reasons, I should help them, right? Because the problems with. But then there's the other thing is, if you ever try to deploy static analysis to people, usually, at least in the contexts that I've been in, their first reaction is, well, I'm not really sure. I've heard that this is quite noisy stuff, right? And then in this case, they're saying, we want it. So it makes sense for the analysis experts to, if you keep saying we want it, we want it, we want it, okay, let's try to give them something that's useful to them. Now I realized I could not make my prover in their time scale. So their time scale was they needed this in months, not a year. And so I pivoted, and I talked to them about what they needed. And two of the important things they needed is, they said, we don't actually need you to prove the absence of all bugs. Just find a lot or most of the bugs, and we'll take responsibility for the rest. Speed us up, they're saying. They said, don't worry about fine-grained concurrency. That's only a very tiny amount of the code. The experts will take care of that. Find all of the easier race bugs. And so we made a program analysis, which is actually not that easy, not a completely easy program analysis, and it tracked things. And it did this kind of race detection. And an example of what it did is it went through all of the procedures, and it would make a summary of each procedure. And the summary information would say, at each program point, if there's a data access, and what the access path is, the syntactic access path, whether a lock is held at that point, if it's on the main thread or not the main thread. And so it then would look at all that information and then decide, does this mean it's a race or not? So what we did is first we make the summaries, then we compare the summaries and decide whether there's races. And so in the cases of the blue, so you've got to write on the main thread and an unprotected read off the main thread. So if we've got to write them on the main thread and the other one's off the main thread, that means they can run in parallel. And if one's protected, the other's unprotected, that means they can race. So then we would report a race in this case. But the interesting thing here that I'm pointing out is first, make summaries. Second, make choices. But the whole design of it actually used an abstract interpretation framework inside of Facebook that this fellow Sam Blackshear had made. So I wrote a little abstract interpreter. Although I wrote the little abstract interpreter, it didn't conform to like a soundness theorem. It used like, we had a widening, we had a join, we had this, but it didn't satisfy the properties that you need to get soundness. And it was easy to make false positives, so it's possible to make false positives. And so, for instance, we didn't even track the identity of blocks. We just said, is there any sync, not lock. So this one, there is a race between those two because those are different locks, so they don't exclude one another, but we wouldn't find it. So there were lots of artificial false negatives. So there were lots of artificial false negatives. Now the analyzer experts, besides me, were really, I was irritated by this, but the analyzer experts were even more irritated. So they started to change the analyzer to make it closer to the sound. So somebody implemented an alias analysis. Somebody implemented an escape analysis. And when we put these into the analyzer, then we get huge blizzards of false positives. Right? So then we said, okay, let's take those out of the analyzer. So then we put it in production, the one that didn't have the soundness there, we put that in production. And lo and behold, it worked incredibly well. I'll come back to that. It worked incredibly well, and it found an incredible number of currency errors. It helps them the programmers take the code and convert it to concurrent code and get a speed up. And so this was a very successful project. So if you remember back to the Engler results, they found 3 race bugs in Linux. Like we found 2,500 race bugs within a year with this, right? This was running scalably, running in the continuous integration system. This was a very successful engineering project. But one thing we did when we reacted to the irritation that doesn't have a theorem, we tried to make it sound over-approximate. Then one day, I said, stop this. We've got an analyzer that's effective in practice. We're trying to change it so that it conforms to the usual theorem, and that's making the analyzer much worse. So why don't we change our minds around the theorem and make that fit the effective analyzer rather than the other way around, rather than make the analyzer worse, make it fit the theory. And so I said, our theorem should be that there are no false positives relative to certain assumptions. And the certain assumptions had to do with some things that were happening in the client code that we were applying it to, not infrastructure code. But it boils down to we were trying to prove a theorem that the analyzer is an under-approximation of the over-approximation. So the over-approximation documented certain assumptions, and then you would have an under-approximation. And it turns out that this theorem was never true of the analyzer, but we took it. This is much more important. Like, the theorem to bless the analyzer afterwards is much less important than the false theorem which influences its design. And so we made design decisions that were consistent with this theorem. And we made a baby version of the analyzer which had it, but the real analyzer never really had this theorem. But this theorem guided the design. So an example is, if I've got x.f and it's owned, so it's local, then I assume x.f.g is also owned. So it's actually false because of the way things can escape to other threads, it's actually false. So we took that as an assumption, and that assumption, which made the analyzer easier, is consistent with the theorem. So the theorem drove us to make certain choices in writing the analyzer that we wouldn't have otherwise done. So that was really interesting. So thinking about this in hindsight, so we wrote 2 papers. So we wrote a practical paper about the analyzer. The first one, which had a very hard time getting in, but the second paper in Popple proved the theorems about an idealized version of the analyzer. The Popple people liked it, and they made comments like, "I can't believe you were able to prove any theorem at all about an unsound analyzer." And this sort of brought I thought, why are they saying this? I mean, it's just an under-approximation of an over-approximation. Well, the kind of thing you should do, use the approximations, and it is. But I realized that a lot of people thought it's just unsound is bad in their minds, right? It's not like there's something to say about the unsound analyzers. There was an idea. It just means it's bad. And I was just scratching my head about that. Maybe we can try to do something about that. And the other thing is that although these papers got in, they didn't generate that much attention, and I was wondering why. And this second paper, although it did prove the theorems, I mean, it's complicated. So it's complicated in details. So we were trying to somewhat match an in-prod analyzer. So it's very hard to take an analyzer that has real impact in practice and write an elegant paper on it. Let me put it like this, I don't know any such papers. I know loads of elegant theory papers that aren't about things in practice, like Hoare's logic. If you don't mind, Cuso 77 is one of my favorite papers of all time, right? So there are theory papers that are very beautiful, and then there are the practical analyzer papers. There are almost none of these to me that are beautiful. I think it's just very, very, very hard to do, and we were in that. We were there. It was very hard to do, so I thought, going forward, maybe I can try to do something simpler and not do something about in-prod and be able to get a message across a little bit better. Okay, so this gets us on to incorrectness, logic, and friends. So I was wanting to do something like this, and I got a prod, and so the prod was, so Derek Dreyer and others were in town, and we were working on a program analyzer to find memory lifetime errors in C++. And Sam Blackshear, my former mentor, had made a version of this based on the lifetime checker, the Borrow checker from Rust. He tried to import those ideas to C++. Blizzard of false positives again, right? Like, the Rust idioms just didn't fit the C++ idioms. And so I reacted very badly to this, like, in 2 ways. Like, why take the least successful part of Rust and import that to C++? But also, the Blizzard of false positives, I didn't like it. And this original bi-induction analyzer that we took into Facebook, I had said many times, why didn't we make an under-approximate version of this? And nobody ever listened, and so I should have done it myself. But then we're in the room, and one person, Jules, was in the room, right? And so then we said, we need an under-approximate version of infer to go after this problem. And he went and he just implemented, without telling us, he just implemented a version of this, and this worked pretty well. And so this got us going. And then it was inferring Hoare triples, but the Hoare triples were found by under-approximation or something that we didn't know. And so then we were thinking, well, we should maybe try to understand the meaning of those triples, which this analyzer seems to work fairly well. So several of us started thinking about this, and there were several proposals. There was an interesting proposal, which will come up later, from Derek and Rob Gillen, when they met us in Lisbon at POPL 2019. But so I was thinking about this, and so I discovered a couple of things which did or didn't match the analyzer exactly, but I thought we're getting in the direction of being very beautiful. This isn't what I wrote. What I'm going to tell you now isn't exactly what I wrote in the POPL paper, because I had this motivation for what to find, and then I found it. Then I took the next step, is like, let's write a paper which doesn't uncover all of that, but just writes it in a way that like as many people as possible can understand it. But now that I've got this kind of audience, I want to reveal that part. And so to reveal that part, I think we have to look at the beauty on the over-approximate side, right? So the beauty on the over-approximate side, so there's the horse triple, right? And there is, well, I guess I would associate that with Floyd, although I don't think Floyd ever used the word invariant. But a superset of the states at each program point, let's call that an invariant. I don't know who used the word for that, but Floyd had that idea in his paper. And then to show that something is an invariant, it's sufficient to find another invariant less than it, right? So if you've got your postcondition Q, you find some stuff that implies Q, with the rule of consequence down at the bottom is the way you say that. You might associate that. But Floyd had these ideas that the over-approximation at every program point. And this is sufficient to prove a program. Very, very beautiful to me. So simple. And then the third part of the triumvirate of beauty, which is Floyd, Moore, and Cousseau, which is that so from the transition system I can make a continuous function, Scott continuous function on a lattice, which just keeps gathering more states. And the reachable things are the least fixed point. X is an invariant, just says that X is bigger than the least fixed point. And so then, we can say this for like lots of arbitrary lattices, not just for this. We can say similar things. So then if we have F over hat is an over approximation of F in the pointwise order, right? Then if I have, if I just calculate the least fixed point of F over hat, however I might do that, an abstract interpreter does that, then I know that that's bigger than the least fixed point of F via monotonicity and the pointwise order. Then I know that that's an invariant of F or of the transition system T. And so calculating this least fixed point for least fixed point of F bar, that gives me a way to prove my program, right? Now, it doesn't give me a way to disprove the program, right? That's the source of false positives. But all of this is just so simple, and so I like these three things I like, right? Unambiguously, I like this stuff. So I didn't say this in the POPL paper, right? Now, so let's just try to redo that with under. So then I just flipped the subset around to say, well, we're going to under-approximate the post, right? There's an equivalent way to say it. And so people have taken this equivalent way to say it, which is that everything in the post comes from something in the pre. People think that have said that this means it's about backwards reasoning. But they couldn't be more wrong, because forwards predicate transformer exists, backwards predicate transformer doesn't. There's a category error people will make, which is states versus predicates. On the predicate level, this thing works beautifully for forwards reasoning, not as easily for backwards. So this is not a backwards reasoning formalism, but anyhow, so backwards predicate transformer doesn't exist. And Hoare's assignment axiom doesn't work. You have to use Floyd's for that reason. So instead of invariants, let's say that a subvariant is a subset of the states reachable at every program point. Then to show that Q is not an invariant, to show that it's incorrect, it's sufficient to find a subvariant which shows that it's incorrect. It's like the testing idea. We find a way to just show that it's incorrect. And it's the same to say something with the under-approximate triple. So these blue bits are what's different from the beautiful bit in the previous slides. The subvariant, and the subvariant gives us a way to disprove, where the invariant gives us a way to prove. then we can do this. We can do all this. We can say x is a subvariant if it's a subset of the least fixed point. This isn't complete dual stuff. If I was to just dualize, I would say x is a subset of the greatest fixed point, right? Like if I'm dualizing, you take least to greatest, but you don't want to do that. The meaning is calculated with the least. So although there's some duality, the theory is not entirely dual, basically because of that. So x is a subvariant. The fact is that if the least fixed point is not less than x, then it's not an invariant. So that gives us a way to disprove. Now, if the least fixed point of the under-approximation is less than x, it doesn't prove that it's invariant, right? So now it's the source of false negatives, not the source of false positives, right? So I'm not saying that this is as beautiful as the previous one, but this is why I worked. Things are lining up here. Things are lining up here like I wanted them to line up, right? So there's one thing is that Joule prodded me because he had an effective analyzer, but this doesn't necessarily fit perfectly in the effective analyzer, but it's lining up with the previous theory that I liked, so I have an opportunity to do that, where we sort of failed in the Racer D theory papers to explain it so that a lot of people would understand it. I thought, okay, now we've got things lining up. And then I took a further step of forget all of this and explain it to people without knowing this, right? But this is what, for me, made everything line up. So, this is very, there's lots of other things to say, but now if I compare the under and over approximate semantics, then I get a diagram like this, and that's the least fixed point of the concrete semantics if f is continuous. Now you see right away that this is just like, oh, I can stop after finite unrollings for under approximation, right? Well, that's immediate from that diagram. If I stop there, it's not sound for over approximation. This is but it's just immediate from that. There's lots and lots of things you can see from this abstract perspective very simply, and so that you know is true. So this is just confirming that it's true. So again, this is lining up. There's much more I can say about the things like this, but I want to move on to the kind of thing you would like to do, which is to use all of this stuff to build I want to build an interprocedural compositional program analyzer. And I want to make a compositional program analyzer, which means it analyzes procedures in isolation. I want to do that because, at least in theory, because if I can do that, then I can run it at PR time very quickly. I can put it in the CI system. If I make a global program analyzer on 10 million lines of code, even if it's linear time, no, I'm not going to be around. It's going to be very difficult to put that in the CI/CD system. So let diag be the diagonal assertion. So it's like true, but it records some things. Then if I take the strongest post condition, then this gives me a way to describe the relational meaning. And so, for instance, if we've got that example, then the capital X is recording the initial value. Then afterwards I get x equals x plus 1, but x is even. But I don't get anything for the else branch because of divergence, right? In this under approximation. So we don't get anything in the else branch. So that calculates that. And so suppose I have something that's an under approximation of post, which is what you want, an under approximation of interpreter. We can have, let me say the words transition subvariant. Podelsky and Rubelchenko talked about transition invariance in their work on determination proving. So this is like a transition subvariant is what it's discovering. That is reading the post. So that's cool. And so all of this is theoretically, it could be the basis for a compositional interprocedural under approximate analysis. It's not what Joule's tool Pulse does, and I'll explain that in a minute, but it could be. So this is quite interesting. So, did I mean to have that as my next slide? Perhaps I did. There's another thing I could have done, and this is what was suggested by Dreyer and Young. But it turns out that Godefroy et al. Had it in Must transitions years ago. But anyhow, instead of under approximating the post, I could under approximate the pre, right? And so there's something called pre predicate transformer, which is the pre-image of a relation. And so it's not the weakest precondition, it's not the weakest literal precondition, it's what's called the weakest possible precondition. I think Hoare called it that. But it's like take the post of the inverse of the relational linear of a program. So an equivalent way to say what this triple means is that everything in the pre can reach something in the post. But it might reach things outside the post too. But everything in the pre can reach something in the post. Now, this, although the equivalent formulation seems to, in the states, encourage you to think forwards, if you think in terms of predicates, well, there's a backwards predicate transformer, namely P, of course, namely pre, which corresponds to this. There's no forwards predicate transformer for this. Okay? The fact is that the fact down there is that it's the same as post on the reverse program, and this means a lot, but maybe not everything. And I think the next talk will be talking something about this. Not everything translates for the under-approximate triples, but a lot of it does. So we could go forward, we could go back. This is where that's quite interesting. So this is where I start thinking, okay, we could do this, we could do that. I'm not sure which is better. I'm starting to get a bit puzzled, but at least as a theorist, I know I could go forward and I could go back. And so then there's something quite interesting which has come up, which is now we're getting beyond my original motivation to some other stuff. So say that we've got a both ways triple if it's sound for the under-approximating the post and sound for under-approximating the pre. So for both. Now this gives what I'm going to call a both ways triple. Azalea observed this. Pulse actually is compatible not only with the forwards under-approximate triple, but also with the backwards under-approximate triple. So all of the steps that Pulse, that's the under-approximate version of phase to confer, is compatible with both of these things. And so she made this observation, and we say it in this paper here. So this is quite interesting. Pulse is not corresponding precisely to this under-approximate theory that I said, but even a tighter version of the theory. What's going on there? Well, what's going on there is that, I didn't say this part. One way to get a both ways triple is to first start from true, or the diagonal relation, under-approximate the post, then go back and under-approximate the pre. Then, via these two steps, you'll get one of these both ways triples. You'll get one of them, but this is not at all the way Pulse operates. So the way Pulse operates is using this thing, abduction, right? And so what abduction does here is it goes forwards, and as it goes forwards, when you hit Boolean conditions, it records the Boolean conditions in the pre while it's generating a pulse. So it's not literally a forwards predicate transformer, but it's something that goes forwards and it records information as it goes along. Pardon me. And so, for instance, if we've got an assumed statement, which is like the branch of an if, and we've got a precondition P, it records B, little b. Now I'm going to rewrite it with capital letters. It records little b as something to throw back to the pre, and it carries it on to the post. For the plus statement, which is like I've got two branches of an if, it union, so it might generate two of these triples, not just one of these triples. So it's doing kind of what's going on here. So as you're going forward, you're shrinking the precondition, and you're generating many such preconditions. So now if I try to just think in very theoretical terms, why would you be doing this shrinking the precondition? Think of this backwards under approximate triple. The backwards under approximate triple, it doesn't have a forwards predicate transform. Right? So given a pre, there doesn't necessarily exist a post. So what Jules is doing in retrospect, what he's doing in retrospect is he's got the pre, but there is no post for the pre. Right? So what he does is he shrinks the pre so that there's a post. Shrink it so that there's a post. Shrink it. So that way you end up in one pass, instead of go forward and back in one pass, you end up getting a triple, which works for the backwards the backwards under-approximation, as well as the forwards. So I think that explains sort of the fact of the matter of what Pulse is doing. We did it with, we did this abduction thing. We just did it. And so why are they doing that? My way of trying to explain now why you do that is if you do want to have this backwards under approximate triple, then you're forced to. You've got to shrink the most. In the old over approximate world, infer was working for the over approximate triple where for safe preconditions only. So again, when there's a pre, there's not necessarily a post. So we're using it. We're forced. We're using abduction to find the safe pre. Here you're using abduction to find the pre when no post exists. Now, there are ways to break the forwards under approximation and the backwards under approximation. And sometimes you might want to do that, but in Pulse right now it happens not to be doing that. So I think I would like to do is good, really. What I wanted to do is to dig. You see, I'm thinking in terms of predicate transformers in most of the motivation and a lot of the things, not necessarily in terms of for logic. So for logic is a good way to explain what the principles of the reasoning are. But really, because I was thinking about program analysis, it's mostly predicate transformers that I was thinking about. Now, we've got this backwards way of going and this forwards way of under approximating. And I see now 3 ways, based on just what I've said right now, to make an interprocedural compositional program analysis. One is this abduction way. The other is with the forwards predicate transformer, generate the post starting from a diagonal. I could do the same thing with the backwards. So this is where there's going to be other talks and there's other people in the audience. I'd just like to confess that it's not so much that I think I don't understand the theory. I think the theory's all, it's just you put together a bunch of stuff and then you try to organize it in your head. There's no difficult math here. I mean, 0 difficult math. Right? But what I don't understand is the ramifications for program analysis of what are good ways to put these things together. So Pulse exists, right? I could now say that I could have made different choices and made other program analyzers that are a bit different. And well, I don't really understand which ways would be best. So I feel like over approximation has been hugely studied, right? Loads and loads of papers, loads and loads of smart people. Under approximation, at least not concrete. So not concrete under approximation has been studied, but much less studied. So we just don't understand it as well because we haven't explored it as much. So I'm not talking about understanding the meta theory. I'm talking about, it's like understanding the grammar of a language and being fluent in the language. So maybe we understand the grammar of under approximation and we're not so fluent in under approximation. So gaining the fluency is where I think we have a lot to learn. Okay? Okay, I'm going to stop there. You picked a good moment to switch off. Oh, no more slides. No.
Great. Yeah, so now we can take questions. Looks like here.
So I was very...
You're very what?
No, it's my microphone that doesn't work. Okay, so I was very intrigued by your theorem on proper because you said it's an under-approximation of an over-approximation. And I think it's not so true. Because if you do further over-approximation and you introduce the true positive in this over-approximation, then when you do the under-approximation, the false positive, you might find this false positive. So it's more subtle. What you do in the over-approximation, does not influence in any way the under-approximation. And then when you do the under-approximation, it doesn't matter which over-approximation you have done. An example would be you have a buffer. You can over-approximate the value that go in the buffer because they don't matter on the incorrectness of the access. And so it's not over-approximation on under, it's some over-approximation that does influence the under, and then a true under which is not influenced, so which is a true under of the semantics. So I think it's rather subtle.
I think it is subtle, and my explanation of it is under, first it's over, then it's under. It's another one. That's why there's no theorem in the paper which says that. And so that's my way of explaining what the theorem should say. But what it does is it takes a program, replaces the program with non-determinism in certain places. So I'm saying that step becomes the thing is over-approximation. Then the resulting program, it really does an under-approximation. So that I don't know if what I just said just agrees with what you said, but
and the under-approximate analysis can have false positives with respect to the concrete.
Oh yes.
Oh, yeah.
Yes, that's correct. Yeah.
And the second point on relational and the post-word give, this exists since '81. And it was implemented by Alvax in the polyhedra analysis by doing a forward analysis and then a projection, you get backward information, and then you can iterate. And maybe you could try to do this iteration to get more precision.
Yeah, I believe. Like, we haven't even implemented one of those for this under-approximate setting. I believe. I think this agrees with me that we've explored much more of this in the over-approximate setting. But I hear what you're saying. For everybody, Patrick's saying if you go back and forth between the back and forward and back and forward, then you can do this to increase precision.
Yeah. Okay, thank you. That was my remarks.
Okay.
All the rest was good work. Yeah, don't worry.
Do we have more questions?
Hi. You in your language for the incorrectness paper, you always use assume statements, right?
Yeah.
Why do you use assume and not assert?
Oh, that's a very interesting question. So I'm saying, like in code assert, I think it says assume this then error. Right? So I think now assume is just to make the if statements work. Right? So that's why. Now, but there's a more comical thing to say, which doesn't have to do with quantum papers, that programmers often use assert like we use assume. So the Facebook programmers will say, assert main thread. And then if the analyzer says, well, you're not on the main thread, no, but I put an assert there because I'm assuming. The programmers very often use assuming, right? If I can encode assert, I don't think I can encode assume. It's all, the programming language is just trying to, just for theoretical minimalism. That's
Hey, Peter.
Greetings, Alexander.
So I was hoping you would have circled back to the concurrency question. So now from the incorrectness perspective, do you think it will be easier to build tools for concurrency?
I'm not sure. Well, Racer D is such a tool, and Azalea et al. Made a concurrent incorrectness separation logic, which I think mostly corresponds to it. So I hope so. I'm not too sure about like fine-grained concurrency, because you end up getting into the details of the interleavings, or worse, worse than interleavings for weak memory. So I don't know if there's any free lunch there, but let me put it like this. For catching a lot of concurrency errors, there's scope for tools that are very scalable and catch a lot of errors. And eraser D just completely proves that point.
Any more questions?
Patrick again?
In the last slide, very interesting last slide. In the last slide, there is a problem with the non-termination because it's not symmetrical. So, in a sense, it does not take non-termination into account, and I think it should be possible. I don't know why. I'm not able to do it, but
Non-termination bound.
yes. So, when you have the relation, you could have also a relation to non-termination. And I have the intuition it's possible to do it both ways also, but I'm not sure.
So, in fact, I think there's going to be a talk today on proving non-termination. So, hopefully that will confirm your intuition.
Any more questions? Okay, great. So let's thank Peter again.